Okay, folks, let's look at example 3. So we're going to solve, or we're going to find the particular solution of the equation d squared y by dx squared plus 2 lots of dy by dx plus 2y equals sin x. Okay, given that x is 0, y is 0, and dy by dx is 0. Okay, so that's our data that we're given, so we'll be able to find every constant that we get. Okay, so however, the starting off process is the same. We've got to find what type of roots we've got and solve it like it's a homogeneous type of question. So we need our auxiliary equation. So auxiliary equation is going to be d squared plus 2d, 2d there, plus 2 equals 0. Okay, so if we solve this, okay, well, I'll look at b squared minus 4ac to work out what types of roots we've got. Okay, that's going to be 4 subtract 4 times 1 times 2, which will give me an answer of negative 4 if I've done that correctly. Okay, therefore, I've got complex roots. So in order to find the roots, I'm going to have to use a quadratic formula. So d is going to equal negative b plus or minus square root b squared minus 4ac, all divided by 2 lots of a. So that's going to be negative 2 plus or minus the square root of negative 4 all over 2. Okay, and then when our square root, negative 4 becomes 2i. So we get negative 2 plus or minus 2i over 2. Therefore, d will be negative 1 plus or minus I. Okay, so we've got both our roots there. So therefore it tells us that the general solution, or the complementary function, so the first part that we would get, complementary function would be y equals, that first number goes to the power on the exponential, so it's e to the negative x, bracket, a cos, because it's just 1i, it's just 1x, plus b sine x. Okay, so I've got my complementary function, and we will need to work out the values of a and b, and we'll work out the values of a and b at the very end. Okay, we'll do the rest of the stuff that we know how to do in the previous exercises, or examples we've shown you. Okay, so next thing is we're going to find our particular integral, so we're going to have to try and solve for the right hand side now. So particular integral, okay, we want to find a function, okay, that is similar to sin x. Okay, that's what we had on the right hand side of our equation. So therefore, we will try y equals, remember we've got to find we've got to take the example, if it's sine, if it's a trigonometric function, we've got to consider both the cos and the sine version of it. Okay, so we'll have c cos x plus b, not b, sorry, let's try it again, should be d sin x. Okay, so that's going to be what our particular integral will look like, y equals c cos x plus d sin x. Okay. So I'm going to want to substitute that into my equation up the top to work out what the values of c and d are. I'm going to do that first. So I'll need to find the derivative of this and the second derivative. So let's go for it. So dy by dx Okay, if I differentiate that, so remember, just be careful with your sines and coses. C cos x will become negative C sin x. Cos changes to negative sine when you differentiate it. Sine changes to positive cos, so that stays positive, so positive d. Oh, made a mistake. Again, cos x. Okay, so that's the first derivative there. dy dx is negative c sin x plus d cos x. We then need d squared y by dx squared. D squared y by dx squared. If I differentiate that again, so sine changes to cos, keeps the sine, so it's going to be negative c cos x. And if I differentiate cos, I do get negative sine, so it's negative d sin x. Okay, so now I've got all my y, my dy by dx, and my d squared y by dx squared. I can now substitute into my formula. So let's do that now. So sub into equation. Okay, so it was d squared y by dx squared, so that's going to be negative c cos x minus d sin x. That was d squared y by dx squared. Then it was plus 2 lots of dy by dx, so plus 2 lots of negative c sin x plus d cos x. Then it was plus 2 lots of y, so plus 2 lots of our function that we started off with, c cos x plus d sin x. Remember, all of that has to equal the right hand side of our equation, which was just sin x. Okay, so again, we need to equate coefficients here, and what we're really trying to do is work out what I've got regarding sin x's and what I've got regarding cos x's. Okay, so if I group all my sin x's together, okay, and if I group all my cos x's together, I'll be able to solve these simultaneous equations here, unless things cancel really nicely. So if I look at my cos x's, okay, if I just look at what cos x's I've got, so if I just look at the cos x, I've got negative c. I've then got, if I multiply out the first lot of brackets, I'm going to have 2 lots of d cos x, so plus 2 lots of d cos x. And then if I multiply out my second bracket, I'm going to have plus 2 lots of c cos x. Okay, so there are all the cos x's combined there. And on the right hand side, I don't have any cos x's, so all that's got to equal 0. Okay, I can tidy that up before I move on. So negative c and plus 2c can cancel, so I'm going to have c plus 2d has to give me 0. Okay, that's what I've got there. So that's I can't solve for that at the minute, but I've got an equation, or I've got a general idea of what the rule would have to be for c and d. Okay, c plus 2d has to equal 0. If I look at the sin x part now, okay, so again, look at all the stuff on the left hand side. I've got negative d lots of sin x first. If I multiply out my first lot of brackets, I'm going to have negative 2c worth of sin x. And the last bracket, I'm going to have plus 2d lots of sin x as well, okay? And that will have to equal how many sin x I have on the right hand side, which is 1. I've got 1 sin x on there, okay? Again, tidy up what I can. So if I combine this, I'm going to have negative 2c plus 1d that I'll have left. That has to equal 1. So you can see I've got 2 equations that I'll have to use to solve simultaneously to get the values of c and d. Okay, so solving simultaneously. Okay, c plus 2d equals 0, and negative 2c plus d equals 1. Okay. This will lead you to solving for c and d, which will give you an answer of c equals negative 2 over 5, and d is 1/5. Okay, so that's the 2 solutions that you would get that would solve those 2 equations there. Okay, back to my general solution now, because I've got the bits I need. So my particular integral is y equals -2/5 cos x plus 1/5 sin x. Okay, so my general solution is my complementary function that I had earlier plus my particular integral, which means that I've got e to the negative x, a cos x plus b sin x, okay, plus my particular integral, which is now not plus anymore, that's because it's -2/5 to start with. -2/5 cos x plus 1/5 sin x. Okay, so that's what we got up to in the previous two examples. We got up to a general solution, but I now have data at the start of my question I can use to find the constants a and b. Okay, so remember this is my general solution for y at the minute. Okay, so the first thing that I've got data-wise is that when x is 0, y is 0. That was one of my stipulations, okay? So I'm going to substitute these in. So if I substitute these in, I'm going to have 0 on the left-hand side. E to the negative x becomes e to the negative 0. A cos 0 plus b sin 0 minus 2/5 cos of 0 plus 1/5 sin of 0. Okay, so I've substituted that in. So a lot of things do vanish, okay, so anything to the power 0 becomes a 1. All the cos's that are at 0 are value 1. Anything that is sine becomes a 0 at 0. Okay, so a lot of things do vanish. So what that comes down to quite nicely is that 0 equals, well, the a cos 0 is going to stay there. So just a, because cos 0 becomes 1. And the minus 2/5. Okay, so 0 equals a minus 2/5. Therefore, what that tells us is that the value for a has to be positive 2/5. Okay, so we've got my value for a. The second thing I now need to do is use the other piece of information, which was dy by dx equals 0. Okay, but in order to do that, I'm going to have to differentiate this function. Okay, and you can see here that I'm going to have a product rule limiter here. Yeah, I've got two functions. I've got an exponential function and a trigonometric function multiplied by each other. So we'll use the product rule there, and I differentiate these separately. Okay, so that's what's going to have to happen here. So dy by dx. Okay, so we know how the product rule works by now. Keep one thing the same, differentiate the other. So if I differentiate e to the negative x, so if I differentiate that one, I'm going to get negative e to the negative x, but I'll keep everything else the same. But I can substitute the value for a in now, because I've worked out a, so that's going to be 2/5 cos x. So I don't know what b is, so that's plus b sin x. Okay, if I keep the exponential the same, I then have to differentiate the trigonometric functions in the bracket. Okay, so cos x changes to negative sin, so it's going to be negative 2/5 sin x. Differentiate b sin x, that's going to give me plus b cos x. Okay, that's me dealt with the product rule part. If I then differentiate the last two terms, so cos becomes negative sin, so the negatives will cancel, they become plus 2/5 sin x. And if I differentiate a 5th sin x, I'm going to get a 5th cos x. Okay, so that's my general solution differentiated, but I've put in the values for a in there. So again, let's go to the data that we had. So it was when x was 0, dy by dx is 0. So that being the case, we're going to have dy by dx is 0, so the left hand side is 0. Again, we've seen a lot of this now before, so you can put 0 in every time you see an x, so I'm going to get 2/5 cos of 0 plus b sin of 0 in there. plus e to negative 0, negative 2/5 sine of 0, plus b cos x, cos 0, plus 2/5 sine of 0, plus a fifth cos of 0. Okay, so we know all the sines of zeros are 0, so they'll all vanish. The exponentials, because they're a power of 0, just become a 1, so do the cos zeros. Let's put that in there, so they all become 1s there. So let's see what I'll have left. So I'm going to have, so we get 0 equals negative 2/5 plus b plus a fifth. Therefore, if I type that up a bit more, I'm going to get negative a fifth plus b. Therefore, b is a fifth. So a particular solution is y equals e to the negative x 2/5 cos x plus 1/5 sin x plus, it wasn't plus, it was minus, sorry, minus 2/5 cos x plus 1/5 sin x. Okay, is that the better now? Yeah. Perfect.